All right, and next up, we're going to have three shorter vignette style talks from starting with Dongwoo Chung, who is visiting us from CETA and the University of Toronto, and then moving on to two current KIPAC members, Josephine Wong and Jaeyoung Kim. And the idea of this next session is that each of our speakers will tell us one specific story about how data-driven discovery has manifested in their own research.
Green greens. All right, thanks, Susan. So hi, my name is Dongwoo Chung. I'm currently at the CETA and the Dunlap Institute. I used to be a PhD student here, 2014 to 2020 under Sarah Church, and also worked a lot with Risa. This is the first time I've been back in this building since I graduated, and this room is terrifying enough to make me want to immediately skip my conclusions. Yeah, I'm not going to actually end the talk here. Rather, I just want to make sure that by the end of this talk, you should take away a flavor of what line intensity mapping, which Simon gave a really nice overview of on Tuesday, is like with non-21 centimeter lines, and in particular how much information they can potentially give us at high redshift from these lines that are typically associated with star-forming galaxies in the far infrared, rest-free far infrared. And in particular, I'll try to give in the last -3 minutes or so that I'll have, I'll give a brief overview of the ways in which we've been thinking about applying certain kinds of statistical methods to modeling and analysis of these kinds of signals. So line intensity mapping, as Simon sort of reviewed, is all about trying to resolve galaxies without resolving individual galaxies. If you just care about the large-scale clustering of matter at high redshift and trying to resolve that in 3 dimensions, you don't necessarily want to be spending time resolving individual galaxies. Rather, you want to be resolving at coarser scales the line emission that they all emit together in aggregate. And this is, we think, a really interesting way to try and fill in a 3-dimensional picture of the universe beyond the spectroscopic galaxy surveys that have been so successful at lower redshift and leading out to the CMB that has been so successful at other epochs. As I said, this is an observation that is, looking across the sky, but also it's going to look across the line of sight because of the nature of line emission allowing for a 3-dimensional redshift space measurement. And so by taking the summary statistics of those line intensity fluctuations, we're not into field level inference quite yet. We want to make inferences that take into account not just the brightest sources that will be detectable individually in surveys from instruments like JWST or ALMA, but we're also thinking about the clustering of fainter sources that aren't detectable in isolation, but in aggregate, they can help us get a fuller picture of what's going on across the cosmic web as it emerges out of ionization. And so by measuring these fluctuations in line intensities across cosmic scales, you're getting a full idea of cosmic processes like ionization and structure formation. So Simon's talk very much focused on the 21 centimeter line from neutral hydrogen. The lines that I think about most of the time are CO and C2. So the rotational transitions of CO trace the excitation of molecular gas in the interstellar medium. And the C2 line is a pretty prominent cooling line in the far infrared. And so that also tends to be associated a lot of the time with star-forming activity in galaxies. It's important to remember that these all trace the same general cosmic structure. At lower redshift, of course, you're looking at the H1 around and in and between galaxies. The CO and C2 very much trace the galaxies themselves. The CO is tracing the fuel for the star formation, the cold molecular gas, while the C2 is more tracing the neutral and ionized phases of the interstellar medium as they interact with the interstellar radiation field. If you go to higher redshift, out to later epochs of ionization, you'll see a scenario where the H1 is still tracing a lot of unionized matter, and then you have the CO and C2 in the centers of these ionizing bubbles. So there's a tremendous amount of complementarity for CO and C2 line intensity mapping. This was first realized, if you really want to trace it back, you can trace it back to the first Billion Years Workshop at Caltech, where there were 2 tech dev programs, one of which became COMAP, one of which became TIME, But I don't think that workshop in particular is really responsible for what we're looking at now, which is the sort of full experimental landscape of experiments that are targeting CO and C2 emission at a range of different redshifts, using all kinds of different techniques. Balloon-based experiments. You heard from Kirit on Tuesday about SPD Slim, and so the experiments that I work on in particular, I should call out COMAP, which I worked on during my thesis. This is the Pathfinder phase of the instrument at the Owens Valley Radio Observatory. TIME, which is an experiment that's targeting epoch ionization C2 from the Arizona Radio Observatory at KIPAC. And there is also CCAT, which is a facility that is serving a number of science cases, including galactic science. There are multiple science cases that benefit from the design of this particular telescope and the size of it, thanks to the low system emissivity, the high side, and the wide field of view. And fortunately, C2 line intensity mapping data side is one of the key science cases. I'd say KIPAC was actually pretty instrumental to the growth of this particular subfield. If you go look for cosmological CO intensity mapping in NASA ADS, number 6 by citation count is this paper written entirely by KIPAC people, looking at applying then state-of-the-art galaxy halo connection models to forecast for COMAP. And so this would not have been possible without support from KIPAC, in particular KIPAC seed funding. The other way in which this was a really nice place in terms of line intensity mapping was that this place actually hosted the first workshop that was about specifically intensity mapping, not just first billion years, not just 21 centimeter, but all kinds of science cases to do with line intensity mapping in H1, CO, C2, Lyman alpha, what have you. So this actually started a series of workshops that have been continuing to this day. So it's very nice to remember that KIPAC was actually pretty instrumental in basically kickstarting what I'm now spending my time doing. So just to sizzle reel up the kind of momentum that's been continuing from that initial impulse, the CMAP Pathfinder is still operating. We've got a series of initial early science papers out, including the first constraint on the CO power spectrum. The cross-correlation analyses that we wanted to do with COMAP are mostly with Lyman alpha emitters, but also quasars. Those are the main galaxies that are observed by redshift 3, which is our current target with COMAP. We have a PhD student at Caltech that's basically doing the analysis with real data that I was forecasting during my PhD. So that's pretty nice. In the future, we want to actually scale up the instrumentation to span multiple frequencies to capture multiple transitions of CO, because not only does that let you get a more robust measurement of the CO at redshift 7 by cross-correlating across different transitions, by getting at those different transitions, you're actually probing the excitation conditions of CO. So you're getting information about, say, CO abundances or molecular gas temperature and density in sort of the cosmic average molecular cloud. Switching gears really quickly, TIME is also doing pretty well. The most recent engineering run, we demonstrated reasonable spectral imaging capabilities. So this is our commissioning image of Sagittarius A, central molecular zone. You can see there's a lot of orange. If you look at the individual channels, you'll see there's a lot of CO flux because it's the central molecular zone. And so thankfully, the NSF have decided to fund TIME through 2026 with an AAG. So we'll return. That allows us to return to peak this winter, and we'll begin science operations soon enough. And then, of course, CCAT is breaking ground literally right now, 5,600 meters above sea level. And the survey for that, when it deploys, will actually result in an order of magnitude improvement above beyond current surveys like TIME. And so it's the 10 times or bust thing again. You want every generation to kind of go 10 times more sensitive. And this is kind of the philosophy that we've been thinking about as we think about the roadmap for line intensity mapping in future. Kirit led this white paper for its SNOMAS process. And the idea is that every 3 to 6 years, if you can get an order of magnitude improvement, you'll eventually scale up to stage 3, stage 4 CMB experiment scale focal planes. But those focal planes will be full of on-chip spectrometers, and there'll be actually very competitive probes of things like primordial non-Gaussianity and dark energy. If you're not interested in what FNL is, then the basic roadmap still looks fairly interesting in that these wide field cosmological line intensity mapping surveys at the end of this roadmap are going to have tremendous potential for cross-correlation in science with Rubin, Desi, Roman. I left out S4 just because I ran out of space. So that's all well and good. But as we get to the bottom of that roadmap, we need to remember that this is sitting at the intersection of high redshift astrophysics and cosmology. It's large-scale structure lit up by star formation processes happening at kiloparsec to even parsec scales. So this is a really busy intersection with a lot of different processes running into each other. So one thing is you need to think about how do you leverage the small-scale picture in the ISM and apply that towards a model of large-scale line intensity fluctuations. The other aspect is that this is a really, really non-Gaussian signal. And so you need to really look beyond the power spectrum, which is what cosmologists are used to. But you need to extract non-Gaussian information to get at some of the astrophysics. So I think a range of statistical techniques are going to play a pretty important role as we address these kinds of questions in the coming decades. So in the negative 3 minutes that I have, I will give just a flavor of what's been going on at CETA in terms of trying to think about these kinds of issues. At CETA, we're actually pretty interested in applying insights from the FIRE suite of simulations, which are resolving individual galaxies with baryonic and feedback prescriptions, and trying to apply that into halo models for line luminosities for line intensity mapping forecasting. So Dick Bond and I, we co-mentored a undergraduate that has been working with a postdoc, Li Zhen Liang, who basically wrote a 42-page paper about C2 and FIRE simulations and came away with a few insights. We decided this was a reasonable basis for a different halo model from what's conventionally done. Instead of linking it directly to star formation rate, we're linking the C2 luminosity through gas mass and gas phase metallicity and modeling it that way. And that allows us to, that allows us to reproduce some trends from the FIRE simulations, statistically speaking. And it also lets us, of course, forecast various kinds of line intensity mapping observables like the power spectrum. But imagine if we didn't have a Li Chen. Imagine if you didn't have someone that was really motivated to write a 42-page paper on C2 and FIRE. Then what do you do? Well, I think we probably could have gotten away with a few alternative approaches, thinking about some kind of dimensionality reduction, thinking of some kind of emulation that would basically directly try and interpolate across the FIRE galaxies to paint onto the halos in the big cosmological blocks in some fashion. These are, of course, really naive ways to think about it, but potentially these kinds of capabilities become more important as you think about, actually, we don't just want to paint FIRE galaxies onto halos. We want to paint all kinds of different prescriptions for baryonic feedback and physics and test them with C2 line intensity mapping. And then that's where I think those kinds of capabilities could potentially become really interesting. I am well over time. Let me just finish off by talking about statistics beyond the power spectrum. The C2 forecast paper, when it comes out, hopefully later this month, will have some discussion of one-point statistics, because that's something the line intensity mapping theorists are now really into in terms of probing non-Gaussianity. However, the other thing you can think about, of course, in terms of probing non-Gaussianity is all these nonlinear convolutional methods. On the simpler side, there being these wavelet scattering transforms. And if you go to a simple Fisher forecast and work things out, you realize the information content in that scattering transform is higher even than the combination of the one-point statistic and the power spectrum. The issue, of course, is that the nonlinearity of that statistic is a double-edged sword. You're going to have more information content thanks to that nonlinearity, but the nonlinearity also screws up your interaction between the signal and the noise. So on the left, you have unreadable plots, and the right, you have unreadable plots. Don't worry about it. The gist of it is that if you have noiseless CO simulations and you tune around your model parameters, the scattering transform coefficients actually respond in really interpretable ways. The issue being that then you introduce noise, and then the signal and the noise interact in non-trivial ways, and then coefficients that shouldn't respond in ways to certain parameters, and then coefficients that should respond don't. And so then you're going to have to rely on simulation-based understanding of how these statistics behave in the presence of different kinds of signal and noise. And so you better be sure you really understand your noise, and you better be sure you really understand your signal, or at least the kind of range that that signal can span. And that means you really need to understand the galaxy halo connection better. And that loops me back to my first point, which means when your talk's looping in on itself, it's probably a good time to end. So I will go back to my conclusions. I think there's been a lot of rapid experimental progress in centimeter-millimeter wave, and there's potential for a lot of information to be, excuse me, there's a lot of potential for information to be derived from these probes. And I think it'll only really be possible for some of the reasons, excuse me, for some of the reasons that I've outlined, with the use of all kinds of different statistical methods, both old and new. So my voice is going. I'll leave it there. Thank you for your patience.
Fantastic. And we have time for questions. Please raise your hand.
So intensity mapping is fantastic, but it's also very complicated because these lines all trace so many different things. Do you think we need a much deeper understanding of these tracers and the galaxy formation aspects before we can really do robust cosmology, or are you not worried about that?
So the Carcarial white paper that I showed, the constraints on FNL, all those other parameters, are, I believe they are marginalizing over the astrophysics at some level. Even if you don't know the fine details, if you're just working at a halo model level, I can imagine that that is sufficient. The issue, I think, in terms of robust cosmology is not actually going to be distinguishing how the lines map onto the structure. It's what structure you're looking at, because the millimeter wave surveys, right, as you're aware, are going to have redshift 6 to 8 C2, and then CO lines at mid to high J from all these different redshifts. So I think the interloper thing is what you should be worried about if you're thinking about cosmology, because then you have different large-scale structures overlapping on top of each other. I think really the way to solve it is by cross-correlating, scaling these surveys up to basically, SPT, S4 scale focal planes, so that you can have hundreds or thousands of square degrees, and then you're cross-correlating with other cosmological probes like Rubin or CMBS4, and getting out more robust signals of electrical structure that way.
Fantastic. Risa stole my question a little bit, but I wonder if, in addition to astrophysical uncertainties and interloper style systematics, are there other data systematics that really scare you and that you think, and what's the path forward? Sort of in the spirit of Elizabeth's talk.
Yeah. Data systematic. What is I have data? I don't think there is anything that's really going to be prohibitive, barring a total failure of your cryostat in the middle of your run or what have you. I think the CMAP folks, for example, have taken a pretty cool approach, and it's working out well for them. They have all kinds of different housekeeping data that they can correlate the data streams with to find out, oh, this systematic's due to this systematic's due to this. So even if they can't control it, or correct for it in post, they can actually, go back and say, well, actually, this, might be a good thing to avoid. And so, I think we're in a pretty good place where a lot of the, a lot of these things can be correlated and found out that way. I think the thing that scares me about these things like time and CCAD are going to be the calibration, because the CMAP, I think, has the advantage that it's working off a coherent amplifier architecture, and so there's a better a sense of calibration. It's an easier sense of calibration than trying to make sure your TES are staying linear all the time. And the superconducting sensors are great, but they have their little quirks, right? Yeah, it's just a really complex system. These are really complex systems with thousands and thousands of superconducting sensors read out by other superconducting sensors, and so I think the best thing you can do is basically keep good housekeeping data, keep good telemetry, and then cross-correlate and figure things out from there.
All right, let's thank Dongwoo again.